The hydrogen atom wave functions can be expressed in spherical coordinates as a function of r, theta, and phi, in terms of two distinct functions, one containing the radial dependence and the other one containing the angular dependence in terms of theta and phi. This is now the general form of the hydrogen wave functions. If we concentrate on the 1s orbital, we can look specifically at the r dependence. The wave function, and let's make sure we understand that this is the wave function for the n equal 1, L equals 0, or 1s orbital, r10, can be expressed in terms of the Bohr radius, a mu, where mu refers to the reduced mass, and then this times 2 times e to the minus r a sub mu. We notice that this exponential will be centered about the origin. In other words, it reaches a maximum at the origin for our wave function. Now, if we do the wave function squared, just simply take the square of this thing, we get exactly what we would expect. As a matter of fact, the proper way to write it is in terms of the norm. In this case, it's a purely real function, so it'll just be the square of it. But we end up with 1 over a sub mu quantity cubed times 4 times e to the minus 2 r over a mu. Again, centered about the origin. So we're left maybe with a doubt. Is the electron located at the origin? And the answer, of course, is no. Why? Because we look at the probability of finding an electron at r. And that, we need to be careful about, introduces this term of r squared. In other words, it goes something like this. Essentially, this is because if we integrate this from 0 to infinity, we would end up with 1. In other words, the electron must be somewhere. Well, if we look at the specific volume interval, in this case, it's not the entire volume, it's just the r dependence of that volume. We end up with the following. R squared dr, which is the what we usually find out put up in the integral, in a spherical integral, and then we have a mu cubed, a sub mu cubed, times 4 times e to the minus 2r over a sub mu. Great. Now let's concentrate on the function itself and look for extrema of this function. At what point is the electron likely to be found, or most likely to be found? For that, we resort, again, as we've done in other cases, to the calculus, and we look specifically at the derivative with respect to r of the function of r, which in this case is ddr of 4 over a sub mu cubed r squared e to the minus 2r over a sub mu. And we set that one equal to 0. Again, we're looking for the extrema. Factor out 4a mu cubed and take the derivative of one term and the other term using our normal rules. 2r times e minus 2 over a sub mu, plus we leave the first term alone, times, now we have the component that comes down from the exponent, minus 2 over a sub mu, times the exponent, e to the minus 2 r over a sub mu. And we close the parentheses. So at this point, then we can factor out, well, let's go ahead and write it down, a sub mu cubed. We factor out the 2, and we have r e to the minus 2 r a sub mu minus r squared over a sub mu times e to the minus 2r over a sub mu. And again, that is equal to 0. We put one expression to the other side, to the left-hand side, and we come up with r squared over a sub mu, e to the minus 2r a sub mu, equals to, and then the right-hand side, r e to the minus 2r over a sub mu. Notice that what we've done here is a little bit of combining here. We came up with an 8, but that's just irrelevant because we have 0 on the other side, so we can divide and multiply and get rid of that term altogether. So we're only left with what's inside the parentheses. Another way of saying it is those are constants. They're not going to be equal to 0, but that right there must be equal to 0. So we set that fellow equal to 0. Again, here now we can cancel out the exponents, and we come up with an expression that looks like this. We can factor out then the r, and we come up with another similar expression to the one up here. We have this r times this term right here equal to 0. The only way that can be true is either this quantity is 0 or this quantity is 0. We don't know what r is, so we can't really specify r equal to 0. But we can say that at r equals to a mu, that quantity goes to 0. So that is what we do. We end up with r equals to a sub mu. So that is the maximum likelihood of finding the electron at a particular r. That would be the Bohr radius. And by the way, the Bohr radius in other derivations is found out to be this expression 4 pi epsilon naught h bar squared over mu e squared. Well, let's go ahead and plug in some values, and we know the expression for a sub mu equals 4 times pi times h bar squared times epsilon naught divided by mu, the reduced mass, times the electron charge squared. We replace the reduced mass with the mass of the electron since the nucleus is so much more heavy than the electron. And we insert these values into the calculation. In passing, we do dimensional analysis to make sure that our units are correct. Notice that we had to go ahead and break down the units of joules to more fundamental units, also newtons and more fundamental units. When we do that, everything cancels out except for 1 m, which is meters. And that is what we're left for our Bohr radius. Bohr radius is a radius measured in meters. Makes sense. So we're in the right path. And that's how we came up with this value for the Bohr radius of 5.29 times 10 to the minus 11 meters. And highlight the point that the initial wave function, the radial wave function, or even the wave function squared, give us these values right here that we've plotted from data points 1 through 48, centered around 0. The origin is around 0. So r, the radial wave function without being squared, is shown in blue here, and we see that it reaches a maximum at the origin at r equals to 0. And similarly for r squared, as expected, it's bigger, but it still reaches the maximum at r equals to 0. So is the electron really at the nucleus? Well, not really. When we look at the probability of finding the electron at r, which introduces this r squared term right here. And assuming an AMU, an a sub mu, a Bohr radius of 1, we notice right here that we multiply r squared times this exponent of minus 2r over a sub mu, and we plot it. This curve right here is exactly that data of r squared times the exponent, and it tells us that the maximum is over here located at 0.11, right around there, at a value of 0.13 in these arbitrary units. So series 1, 0.11, if we look at 0.11, that comes out to be this one right here, and we notice that we have r equals to 1, which is 1 AMU. So the radius of 1 AMU is the maximum right here. So that's exactly what we're seeing, that the Bohr radius is actually where this function is the maximum. And that's the difference between the probability of finding the electron at r versus the wave function and where it reaches its maximum value.